from yesterday? Any questions from anything? So it's Monday. Yes, Monday. The exam will be, let me put that in the message too. Monday exam at 10, email. I'll put that in the email out. Okay. Okay. No questions. So today we talked. Okay, so we started with kind of simple stuff, distributions and means and variance. Then we learned some of the basics of regression. We learned what our regression coefficients mean. We learned what happens as we control for additional things, how to interpret those. We learned about interaction terms. We learned about omitted variables bias, which is probably the core concept of the class. And then recently we were learning about statistical inference. So how do we tell whether an estimate that we have is statistically significant or whether it's consistent with there being no effect at all or no slope at all in the regression. Today I'm going to try to do probably 2 decks. Let's see how long this deck is. We'll just see how it goes. And happy to we'll just see how it goes, and we can either go do some homework together or we can get through two lectures today. I wish I had a version of this that had less junk in it, but let's see. So today's just practical considerations, things that we need to know about our regressions that aren't immediately obvious. So let me do one thing really quick. I am just going to clean this up because I thought I had already done that. And it can be distracting. Do any of you have children? No? It's probably smart not to have kids while you're in school, while you're in undergrad anyway. But they're very fun, but they don't care when you're at work. They just don't care. I think last time I taught this class, I had 2 women that had kids at home. And one of them, she's applying for the PhD program here, so that's kind of fun. She was a good student. Okay. Okay. Okay, that's good. Okay, So these are just some things to keep in mind when we're doing regressions. So the three main items. One is outliers in the data. So you've probably heard someone debate and they say, oh, you know, such and such and such and such and such. And they'll say, well, such and such is an outlier, by which they mean it's kind of a weird data point that doesn't really apply. In statistics, one of the interesting things is, say we had a bunch of data like this, okay? And so if we just drew a little line through it, through this data, we'd get something like that. Sometimes we have an outlier that looks like this. So it's usually very far away in the x-axis and very far away in the y-axis from the other data. And so if you drew a line through these points, you actually would get something slightly different. You wouldn't get something as flat, you'd get something kind of one like this between those points. And so sometimes our question is, do we include this data point in the regression or not? Do we feel more comfortable with these guys, these data points down here, or do we think actually this outlier might be an important feature to kind of use to predict? So the other kind of related question actually is, say we had, you know, we have what's a good example? Okay, so say we had a bunch of high school students, and most of the high school students are, you know, we're predicting their income, and most of our high school students are like between 5 foot and 6 foot. And we're predicting their, I don't know, we're predicting their adult marriage rates by their height. This will just be all boys. We'll do all boys. This won't be the girls. Okay. So maybe the marriage rates are higher for taller men than for shorter men. And so we would, if we were doing a regression, we would draw a line through the middle of those points. And the question is, what if I tell you that about there's a person in the neighboring high school, and he is, sorry, I did that wrong. And he is 7 feet, okay? Can we predict the marriage rate of this 7 foot person based on the marriage rates of these people within the 5 to 6 range? And the answer is, it's not totally clear. It's not totally clear that this could be a linear relationship. So let me give you one example. What if this right here is 100% marriage rate, okay? So say we're predicting for this 7 foot person that he is 110% likely to be married. Well, clearly that doesn't really make any sense. You can't be more than 100% likely to become married. So that would be kind of an example of that. Another thing could be that that out of sample, very, you know, so I think what we tend to find is that there's a peak. So if we found more data, more people that were very tall, we'd actually find that it's not a linear relationship everywhere. It's actually a curved relationship, so that the prediction up here is likely to be wrong. So that if there's a curve, or if it's predicting something that doesn't make sense, predicting out of sample can be kind of tricky. Okay, and then finally, functional form of specification is when we're not allowing for the data to speak. We're imposing a constraint on the data that prevents it from really saying something clearly. So we'll do some examples of that as well. So in a data set, there are often outliers. And an outlier is just any observation in the data. That means any row in a data set that will have much smaller or larger values than is typical in the data. And we have to kind of think about how we handle these outliers when we conduct our statistical analyses. So why do outliers occur? Sometimes there are coding errors. We'll go over all of these, but there can be coding errors. Sometimes there can be just like very, what you might call very unusual people or firms or countries. Okay. So you can imagine like an outlier would be Mozart. Okay, Mozart was playing piano for 16 hours a day since the time he was 3 or 4. So he was an outlier. And if you just had a data set of how many hours every person is playing musical instruments, he would be this. Most people are playing musical instruments, between 0 and 1 hour a day. And maybe a few hundred hours over the course of a lifetime. And he's playing tens of thousands of hours. So he'd be very, very unusual, very strange. Strange in the good way. Why and when should we be concerned about outliers? We're not totally, so if they are coding errors, it can cause our estimates to be wrong. Okay. So sometimes, like, I could do a survey of all of you kids. I could send out a paper survey, and sometimes your writing is hard to read, maybe. And so I could have a research assistant be typing in all the information, and they misread something or they mistype something. That's not a reflection of the true world. So if there's an outlier that is the result of adding an additional 0 to 100, so it's 1,000 instead of 100, which would be a normal variable, we can get really wrong answers. And how do we address outliers in practice? So typically we're going to usually be interested in seeing how sensitive an estimate is when we exclude an outlier. Okay. So outliers typically occur for 2 reasons. The first reason is that they're just a mistake in the data. And it's very common to just have too many zeros in a particular, when we code wrong. I'm trying to put in 100 and I accidentally tap the 0 one additional time. These are easy to fix. You can either correct the data, if you can find the original source, or you can just drop the observation. Dropping the observation is kind of, what's the right word? It can be fishy. So say you did a regression and didn't give you what you wanted to show. You could start dropping observations that push towards this thing that you didn't want to find. So dropping observations is kind of it's complicated. You can do it sometimes, but also you want to make sure that you would be doing it no matter what. You'd be dropping these observations no matter what. So I remember there's a great story. Dan Ariely is this very peculiar behavioral economist at Duke. And he had a person come into one of his experiments who was drunk, and from the street, like a homeless drunk person. And so they were this very strange, in the experiment, they were just like a big outlier. I can't remember what the outcome was, but they scored very low or something like that. And he talked about how it was kind of this conundrum what to do with this one strange observation, because on the one hand, including this person in the data made the results actually look bigger, because he was this homeless drunk person was an outlier in the data in the direction that he thought was interesting. So that's kind of just like a thing. It's not totally clear that we want to drop outliers unless we're totally certain that they're wrong. Okay, there are almost always mistakes in data. If these mistakes are not outliers, they're not as big of an issue if they're included, but they're still a problem. So the thing that we'll learn is that an outlier can have an enormous impact on a coefficient. So remember, we have these betas, which are our slopes. Our beta 1 is a slope. If you have one little outlier, it can change that slope dramatically, depending on depending on how far that outlier is from the mean of X. Sorry, my son's being a velociraptor in the hallway. So an observation is different from other observations in real ways. For example, a very rich person or a very large company will be an outlier in the data. They're, for instance, if we have X, one of the X's is income, their income might be very different than other X's in the data set. I didn't answer this, but even if the mistakes are not outliers, they can be an issue for our estimation, and that's just because we're introducing measurement error into our regression. So normally we've been kind of assuming that when we have a data set, we've got, so let me just give you an example. Say we've got a relationship that's true like this. Here's the relationship between Y and X. Now, what if I miscode this value? This value is X, so that I actually gave it. I typed into my Excel spreadsheet a very low value of X. So instead of putting it there, I put it right here. So that's going to have a big effect on the slope that we estimate. So the original slope would have been something like this, and the slope that comes after it, if we miscode the X of that data point, it will be something like this. That outlier is going to pull up the bottom and push down the top. Okay, so that's just an example of what miscoding the data will do in a kind of extreme example. So why should we be concerned about outliers? So ordinary least squares is kind of the workhorse tool that economists use to understand relationships between variables. And what OLS is trying to do is minimize the sum of squared errors. So that's minimizing the squared error term. Minimizing you might have seen it like this, the squared error term. Because the expression is squared, it gives a greater weight to outliers. Suppose we have an outlier observation of Y, the seventh observation in Y is 20, and the predicted Y for the seventh observation is 10. What happens to the sum of squared residuals if we change the regression line so that Y hat is 11? So just one sec here. Okay, so what we're gonna, let me just fix this. So the idea here is that little differences in the predicted Y hat are going to have a big difference on the SSR, on the sum of squared residuals. So, so here, the squared residual, if Y7 is equal to 10 is the true value minus the predicted value squared. So that's 10 squared is 100. Or what's the squared residual if Y7 is equal to 11? That doesn't seem like a big difference, but it actually will produce a big difference. So the sum of squared residual here will be 81. So one little change in the predicted value will reduce the sum of squared residuals. One unit change in the predicted value will change the sum of squared residuals by 19 units. So that's a very big difference. So what that's really saying is that that these outliers are going to put a lot of pressure on the regression to fit the outlier instead of the rest of the data. So now consider a smaller observation with so that Y4 equals 6 and y hat equals 3, what happens to the SSR if we change the regression line such that the predicted value is 4 instead of 3? So we can do that too. Let me see. Let me just shift this up a little bit. So we're going to do, what's the SSR if y4 equals 6? I'm sorry, 3. We're going to get that it's 6 minus 3 squared is equal to 3 squared, which is 9. And y, if the predicted y is 4 instead, we're going to get 6 minus 2 squared, which is, I'm sorry, that's wrong, 4, is 4. So for a 1 unit change, when the y is less different than the y hat, we only get an additional, we reduce it only by 5. So all that is to say is that outliers are going to have a much bigger effect on pulling the predicted values towards, so small changes in the predicted values will have a much bigger effect on the sum of squared residuals for outliers than for typical values. Why do I say that this is a typical value? Because 6 and 3 are not very far apart. The predicted value and the actual y are not very far apart. This looks like an outlier because the predicted value is quite different than the actual value of y. So let me stop there. I feel like I've been a word vomiting. Questions here, let's check in. Esmeralda, Ibrahim, Katrina, Kimberly, Levi, Luis. Okay. Sounds good. Sounds great. Okay. So when should we be concerned about outliers? As a general rule, we should be concerned about them anytime that the exclusion of a single or small fraction of observations results in a very different regression line. So what does that mean in other words? If omitting a single observation has a big effect on our estimates, that's a outlier that we really want to think about. This is most likely to occur when 2 conditions are satisfied. 1, our data has a small number of observations, and 2, the outlier is very different from the typical observation. This doesn't mean that the regression line is necessarily wrong, or that the outlier should be excluded, but rather it needs careful inspection and consideration. So how do we address these outliers in practice? We can do a couple things. One is to trim. And trimming is just like it sounds. Like if you had a garden and you were trimming your bushes, it means to cut or to drop the outlier observations. And so often what you'll do is you'll say, anything that's above the 99th percentile in X or below the first percentile in X, we're just going to ignore those observations. So we're just going to drop the highest and lowest, 1% or 0.1% of those observations. Another thing that people do that's kind of cool is called Windsorizing. And Windsorizing is a way of keeping the data, the outlier in, but making the outlier less influential in the estimate. So what we do is we change the outlier observation, and so say, like let me give you an example. Say we had, so say we had IQ or something like that. Got this distribution, and we don't want outliers in these tails to really influence the regression. So what we could do is we can say if you're below the first percentile or you're above the 99th percentile, we're going to assign you the value at the 99th percentile. So say the 99th percentile here is like 150. So if you have a IQ above 150, we're going to set your IQ in the data to 150. And if you have an IQ below 50, we're going to set your IQ to 50. So it's called Winsorizing. It's just to set the highest X percent to the 100 minus X percent value and the lowest X percent to the X percent value. So here our 50, our 1% value was 50, and our 99% value was 50, 150. So we're just setting all of the values above 150 to 50, all the values below 50 to 50. So what you choose to do depends on whether you think the data are wrong, in which case you would trim them, or correct but given too much importance. And in that case, you would Winsorize them. Alternative functional forms, you can take the natural log of the outcome. Recall our outlier example there. So that's another thing that you can do is instead of Winsorizing or trimming, you can use the natural log. So the natural log is a cool function like this. And it gets kind of flat as it gets big. And so what that does, why that's kind of cool, is that it's going to compress really big values of X to smaller values of log of X. So say we had some, X's that were way out there, hundreds of millions of dollars, in savings or whatever. That the natural log function is going to be compressing it into a smaller space at very high values. The one problem is that for very low values, it's actually going to be making it into a larger space. So if we have values that are between 0 and 1, the value of the natural log will go to negative infinity as you approach 0. You approach 0, this gets negative very fast. So it's mostly good for kind of working on outliers that are big rather than small. Questions on trimming or Winsorizing or natural log? Okay. So this is a great example. So here's some data. We've got firm sales on the x-axis. There you go. We got firm sales down here. These are firm sales. And this is R&D as a percentage of sales. So how much R&D they do and how many sales do they do. And let's, just for a second, let's ignore this outlier out here. I'm going to say, let's just imagine for a minute that it didn't exist. If we drew a line through these data points, what would we probably draw? I'm guessing we would draw something like this. And then you can think about how would we redraw that line if we were going to try to fit a line through all of these points. I'm guessing that we would draw something like this. Oh, I should draw that in a different color. I'm going to fit these, I think, in the next slide. So don't worry, but obviously this slope and this slope are super different. And so we really would like to know which one is the better one to use. Okay. So we want to estimate the effect of company sales and profit margins on the amount of research and development a company conducts. And the outcome variable is the percentage of sales spent on R&D. So it's basically how much R&D do they do as a fraction of everything that they sell, as a fraction of their revenue from sales. So in this data, we're going to have 32 companies, and we'll have the following estimates. So R&D as a fraction of sales, is that right? R&D is a percentage of sales spent on R&D, yeah. is 2.6% plus 0.00053 times sales plus 0.043446 times profit margins. And we'll just do like a little bit of thinking about this. So N is 32 and the R squared here is 7%. So basically we're explaining 7%, 7.6% of the variation in R&D as a percentage of sales with this model. Let me just show, we'll do a little bit of what we did yesterday, which is some eyeballing. Is this statistically significant? Significant? The answer is no, because the coefficient is not much larger than the standard error. So this isn't going to be statistically significant, different than 0. And the same logic is that the profit margin coefficient is neither significant. The coefficient is not much larger than the standard error. So are the effects of sales and profit margins statistically significant at the 95% confidence interval? The answer is no. Remember, to get something that's about 95%, that's significant at the 95% level, you have 95% means T-stat needs to be approximately larger than 2. And here, this T-stat, remember the T-stat is just 0.000053 minus 0 divided by 0.000044. That's going to be something like 1.2. So that's going to be lower than 2. And 0.0446 minus 0 divided by 0.0462 is going to be something pretty close to 1. So both of those are less than 2. That's what we're doing when we say something is not statistically significant. So what do we learn from the R squared? We learned that we're explaining about 7% of the variation in RD as a percentage of sales with this model. So it's explaining not too much, not a little, but not very much. So this is what the line looks like when we're just doing a regression on the full data. Let me see if there's a question handy. Yeah, so for a natural log, you often use it when you have like income or, yeah, because income is just really skewed. So there's lots of people that earn in the middle, and then there's a few people that are earning kind of massive amounts. And that makes it just a nice place for using natural log because it tends to compress the distribution at the high end. So it's just easier to use in a regression when the data are kind of closer together. Okay, so this is what it will look like. So now what we're going to do is we're going to drop that outlier that we had in that last figure. So we're going to drop this one right here. Let's drop this guy and see what happens. Oops. So now what we find is a slightly different model, which is that the percent of sales spent on R&D is 2.3% plus 0.000186 times sales plus 0.0478 times the profit margin. Okay, so interesting thing. So now we have our sample size is 1 fewer. So it used to be 32, now it's 31. Why? Because we've dropped the outlier. And look at this, the R squared used to be 0.076. Now it's 0.17. So it's more than twice as large. So we're explaining more than twice as much of the variation in R&D using this model if we ignore the outlier. So now, are the coefficients on sales and profit margins statistically significant at the 95% level? Well, we can do the math for these. So here, we're going to find the t statistic for sales will be 0.000186 divided by 0.000084. 0 on top. Let me just do that really quick. So we're going to get that this is equal to 2.2. So is that statistically significant at the 5% level? What do you think? Yes or no? Yes or no? Put it in chat. And you could privately do it if you don't want everyone to see it. Yes or no? Si, senor. Yes. Okay, awesome. So why is it? Because the critical value for 95% confidence is around 2. Okay, so 2.2, our t-statistic is larger than the critical value. This one is significant. So in regressions, we'll often put stars next to the things that are significant. Is this one significant? No. If we divided 0.047 by 0.044, you would get something close to 1, and 1 is less than 2. So that one is not significant. What do we learn from the R-squared? We learned we're able to fit the model a lot better without the outlier. And that will be true in general. Outliers make it difficult for a model to fit. Why do these changes occur? So first of all, the outlier is introducing more variation in Y and more variation in Y that can't be fitted by the model. So that's why the R-squared is going up when we drop the outlier. And the outlier, one of the things that is kind of, maybe we'll see in the next figure here. So you can see here that sales, remember we had the line before when there was the outlier out here was pretty much flatter. So when we ignore the outlier, it gives us a much steeper line. So that's the other thing that's going on, is that the outlier was kind of making it hard for, it was dragging this line a lot. It was having a huge influence on the slope. And so you can see, they're just very different answers. So it's not totally clear which is the right one in my opinion. So now we can also take the natural log of R&D and sales and hope that this better captures the true relationship between R&D and sales. So how do we interpret beta 1 here? Beta 1 is the percent increase in R&D for a 1% increase in sales. Okay, that's what beta 1 means. Beta 2 is the percent increase in R&D for a unit increase in profit margin. So the basics here is that whenever we have log, it's going to make it means that we're talking about percentages instead of units. Whenever we have levels instead of log, it's about units. So that's why here, the coefficient beta 2 is the percent increase, because it's the outcome variable is a log in R&D for a unit increase in profit margins, because it's not a log. This is a percent in the beta 1 is a percent increase in R&D, because the outcome variable is in log, on a percent increase in sales, because sales is in log. So all log is doing is making it so that the interpretation of that variable in the sentence is in percentage terms rather than in levels. Okay. Questions? Questions there? Okay. So now, this is kind of cool. So we have all of 32 companies in the data, and we've logged sales, and we've logged R&D, by which I mean we've taken the natural log of R&D and the natural log of sales, and we rerun the regression. So this is pretty cool. Here we have that the log of R&D is equal to -4.3 plus 1.0 times the log of sales plus 0.027 times profit margins. You can see that our N is 32 because we haven't dropped the outlier, and that the R squared is 91%. So we're explaining 91% of the variation in log R&D with this model. So that's very, very cool. When we drop the outlier, notice this. None of the coefficients change very much. They all change a little bit, but they're changing by not very much. The R squared doesn't change very much. We go from a 91.8% of the variation explained to 90.3% of the variation explained. So when we take the natural log, it is not, we're just, it's that outlier is no longer an outlier. So is taking the natural log fix the outlier problem? The answer is yes. Why do I say yes? Because that one observation is no longer having a significant effect on the slopes or the R squared. Adding or subtracting it does not have a significant effect on the slopes or the R squared, so it has quote unquote fixed the outlier problem. Are the coefficients on sales significant at the 5% level? Let's do a little math. So what was the critical value for the 95% level? It's 2. Okay, so this, the first one, the t statistic is going to be 1.082 minus 0 divided by 0.062. So this is going to be some number well in excess of 2. 1.082 divided by 0.062. That's going to give us 17.4. So it's very significant. It's well above 2. The other one, 0.0217 divided by 0.0128, it's going to be 0.0217 divided by 0.028. It's going to be 1.69. So that's not significant. Okay. What do we learn from the R squared? We learned that the outlier isn't really affecting the R squared very much anymore. Okay, so that's just great. That's a very fun example. So prediction is one of the primary uses and objectives of regression analysis. So if you go and work for Netflix, you're trying to predict which shows your subscribers would enjoy. Because what you're trying to do is give them value. You're trying to recommend to them. They've got thousands of shows on there. It might, if you recommend a documentary about Bing Crosby to someone that loves hard metal, that's just like you're not matching them to the content that they'd be interested in. So you're going to use X's about the person, what they've watched in the past. Maybe you have some demographic information on every person, their age, their sex, where in the country they live, and you can use that to help predict which other shows they might enjoy. What are other good examples? A lot of them are in tech right now. So Amazon is doing a similar thing where they're trying to recommend, say you're looking at children's books and you like Stregonona, one of my kids' favorite children's books. If we go on and we've looked at Stregonona, they might recommend to us books that other people that like Stregonona also like. Okay, given values of the x's will predict the y values, and when the prediction is working well, it means that we're able to predict y values based on x's that are similar to the x's in our data. And the problem is if the prediction is poor, which means that there are big residuals. So say I'm predicting that Devin would like the show Troll Hunters, Tales of Arcadia, which is a great show. But actually he would hate Tales of Arcadia. He hates like, you know, adventure shows or something like that. Then obviously the prediction model isn't working very well. And typically bad prediction takes place for two reasons. One is the functional form might be wrong. So it might be that we're using a straight line when we would need a curve or some other nonlinear relationship between variables to predict well. Or there are omitted variables, observations with very different X values may be different in other ways. So maybe I have a person in the data that looks like Devin in a lot of ways. He's young, he's smart, he's going places, but there are unobservable things about them that Devin likes punk rock, and the person that looks like Devin that liked Troll Hunters loves sci-fi or something like that. Okay. So often out of sample prediction is just not going to work very well. So typically we don't like it when people try to extrapolate from outside of the domain of their data. So say I had your grades in high school and I could predict your income at age 40 based on your grades in high school. And then I said, well, I don't have their grades in high school, but I do have their grades in college. Say I could look at your other grades. Would it be appropriate for me to use the prediction model from high school to predict your grades using your college grades? Probably not, because these are different. I'm predicting based on what wasn't in the sample that I was able to estimate from. So let's do a little example. Oh, actually, let's take a little break. I didn't realize it was so late. Let me take a break and I will get some water. I'll be right back.